Thank you for joining us for this presentation. My name is Moira Poggi, and I'm a geophysicist with HGI, Hydrogeophysics, in Tucson, Arizona. I'll be walking you through electrofacies mapping of the Santa Cruz and San Pedro alluvial floodplains with multiple geoelectrical methods today. Our investigation is centered in the southwest United States in two alluvial floodplains. Throughout this presentation, I'll give you an overview of electrofacies, background of the two floodplains that we surveyed, discuss the survey results, and wrap up with our findings and project comparisons. Our application of electrical geophysics to these floodplains may assist in sediment delineation and water resource identification. Note that the floodplains of interest are within watersheds 8 and 9 in the bottom of the image. Both rivers flow south to north. The Santa Cruz River no longer hosts perennial stream flow and is now an ephemeral flow. The San Pedro River has a perennial flow, and its seasonal flooding impacted data collection during the survey. The geomorphological characteristics are similar between the two rivers, though the location of data collection with respect to the stream bed differed between the two surveys. For our Santa Cruz River study, we collected data to the west of the current reach. The Santa Cruz has levees and barriers upstream to prevent flooding and to protect adjacent agricultural areas from increased meander of the river. This has resulted in heavily incised stream channeling accompanied by piping and sinkholes on adjacent banks. Within our survey areas, channel incision is less pronounced for the San Pedro than for the Santa Cruz. In contrast, the San Pedro geophysical study captured both banks of the river and the stream bed. Our field site within the San Pedro River study was characterized by fluvial terraces and backfilled floodplain, which will be visible in the geophysical data later on in the presentation. Within our survey areas, the incising of the stream channel is less dramatic for our San Pedro study than it is for the Santa Cruz study. Parker and Huckleberry described the Santa Cruz and San Pedro geomorphology in their respective papers. The general definition of facies is, in Nunendorf et al. And others in 2005, the aspect, appearance, and characteristics of a rock unit which usually reflects the conditions of its origin and is different from adjacent associated units. Some type of facies are sedimentary facies, a body with unique lithology like lithofacies, biofacies, which are a unique assemblage of fossil organisms, and electrofacies, which are unique characteristics of rock physical properties that describe its mineral composition and interstitial fluid. We are using surface-based electrical resistivity to map electrofacies, which can be affected by the thickness of the rock unit, the depth of the rock unit, distinctive electrical properties, or regularization in the inversion model, to name a few. Electrofacies won't necessarily match to other facies like lithofacies. The geology of our sites is indicated here from youngest to oldest. In the Santa Cruz River floodplain, continental sedimentation, volcanism, plutonism all characterize the lower Tinaja beds and the Pantano Formation, as described in studies by Davidson. Block faulting helped form the upper and middle Tinaja beds as described in studies by Anderson. These beds are comprised of siltstone, mudstone, and clays. The quaternary deposition of the Fort Lowell Formation was a result of floodplain drainage. Undifferentiated alluvium at the surface is dotted with extensive sinkholes and piping. Eberly and Stanley further discussed this Cenozoic stratigraphy of southwestern Arizona. In the San Pedro, we collected data within the northernmost subwatershed, the Benson subwatershed, over a trough with a thick sandy alluvium which covered the St. David Clay Formation. The depth to the St. David Clay Formation varies extensively throughout the San Pedro River floodplain, which is described in studies by Perthree and Cook. Eroded basin fill contributed to the Pleistocene terrace deposits at greater depths. The deepest zones investigated by our survey are Pliocene playa deposits. The Arizona Water Rights Settlement Act allocated water rights within the Tucson Active Management Area to the Tohono O'odham Nation, which has almost 3,000 acres of active farmland in the AMA. Other operations include the water-intensive production of pecans, which occupies 4,500 acres of land upstream to the south of our survey area, and mining. Here, agricultural areas are indicated in green, and the Mission copper mine is indicated in the large purple zone to the south of the survey area. The mine had an annual water consumption greater than 1,000 acre-feet per year between 2001 and 2005. The land use map indicates a diversity of residential, agricultural, industrial applications and infrastructure around the Santa Cruz survey area. During the early 1900s, mining and livestock dominated land use in the San Pedro watershed, coincident with a population boom in the region. The area suffered from increased flooding, which corresponded to an increased entrenchment of the river. Changes in recent years have curtailed irrigation pumping in the region and turned to managed recharge along the San Pedro. The Cochise Conservation and Recharge Network was established in 2015 and works to establish recharge sites surrounding the San Pedro Riparian National Conservation Area. Gungle and others described the stakeholder and watershed dynamics of the river and evaluated sustainable groundwater use. They noted a cone of depression at Fort Huachuca due to large pumping demands. Upstream pumping at Fort Huachuca, agriculture, and retirement communities in Sierra Vista dominate current land use. Binational agreements have established cross-border aquifer studies on the San Pedro, as the headwaters are in Cananea, Mexico. In Mexico, the San Pedro land use is predominantly for tourism, mining, and agriculture. Our survey requirements called for broad characterization of the Santa Cruz area and finer resolution for the San Pedro River floodplain area. Thus, the electrode spacing of the Santa Cruz is double that of the San Pedro, and our total line distance of coverage for the Santa Cruz was almost 4.5 times that of the San Pedro. We hope to characterize the depth and lateral extent of targets, sandy versus clay lithology using electrical resistivity, and in quantifying the charge storage capacity of earth materials, we hoped induced polarization data would help identify moderately clayey material, like sandy clay, to augment our understanding of any conductive anomalies identified in the resistivity data, to in turn guide well placement. For the Santa Cruz study, there was a priori information for wells and core holes in the area, but we were not able to drill to ground truth along the survey lines. The opposite was true for the San Pedro study, where we received drilling results along the lines after collecting the geophysical data. You'll see those comparisons later on in the presentation. On the left, we have survey line locations for the Santa Cruz River study in blue and previous well locations as categorized by their productivity. Colored dots indicate the productivity of wells, with the green dots indicating production greater than 1,000 gallons per minute. On the right, we have the superficial geology dominated by recent abandoned alluvial fans to the west and historically abandoned stream terraces to the east. Draw your eyes to the center plot. Our survey lines may correlate to a paleo channel associated with a pre-1871 headcut along the river. The pathway of this headcut roughly aligns with the wells that have been good producers and may align with some of our resistivity survey results. Our survey lines are plotted here on top of the map of the historical headcut. The Santa Cruz floodplain electrical resistivity results are presented here in profile form, with the surface distance along the x-axis and the elevation of the lines along the y-axis. Low resistivity zones are indicated by dark blue hues, and high resistivity zones are indicated by red and orange hues. Some of these lines cross through an area of the Santa Cruz River floodplain that historically hosted a headcut of the river. Those zones on lines 1, 2, and 4 are highlighted by boxes with dashed lines. The resistivity data in the vicinity of an interstate overpass are hatched in red to indicate low confidence of the results in these zones due to concrete, rebar, or other infrastructure. As we take a closer look at one of the survey line results, The electrofacies system is predominantly 3 layers: a thin conductive layer on the surface, underlain by a resistive layer of variable thickness, and a thicker conductive layer at depth. The variable resistive layer thins near the center of the line, adjacent to a shallower conductive zone. The resistive thinning is coincident with the location of the aforementioned headcut of the Santa Cruz. It also correlates with a well located 60 feet south of the line, which produces at 1,000 gallons per minute. A similar decreased resistive thickness appears to correlate with a second high production well located 375 feet south of the line. While the conductive zone may correspond to better water production in this zone, the lithology from the drill logs does not provide a direct comparison of gravels and clays to resistive or conductive values. In comparison, our line 4 also intersected the path of the previous Santa Cruz headcut, again indicated by the dashed box. In the previous line, we saw the thin resistive layer along the headcut path adjacent to a shallower conductive zone. Those same characteristics are present here on the right side of the dashed box. The stratigraphy horizons in the closest core hole are similar to the 3-layer system of electrofacies mentioned previously. However, the elevations of the lithofacies do not correspond precisely to the depths of the electrofacies. This may be related to the distance of the core hole from the electrical resistivity line, or the lack of direct correlation of the electrofacies with the lithology due to variations in geochemistry of the subsurface layers. The only well close to line 4 is a moderate producer. The electrofacies along the line do not match the characteristics of the subsurface associated with the higher production wells. The electrofacies identified in the Santa Cruz project can further inform the mapping of the historical headcut and potentially areas of better water resource extraction, as inferred from the production capacity of current wells. We'll explore this further in the San Pedro example. We collected data across the perennial San Pedro River channel and captured the character of electrofacies with both resistivity and IP. The electrical resistivity survey revealed a low resistivity massive clay unit across the site, identified as the St. David Formation. The electrofacies indicated the unit was shallower in the north and south of the survey area and deeper beneath the floodplain of the San Pedro River. Beneath the floodplain, a low elevation channel is consistent across all lines and deepens toward the northwest. Where the clay unit is close to the surface in the southeast, the topography of the buried erosional clay surface may vary by up to 20 feet. It may be possible that channeling exists within the clay unit. This final map was created to highlight the shape of the clay elevation as interpreted from the resistivity and can be shown here in red. Here the resistivity data are shown on top with low resistivity areas shown in blue hues and high resistivity areas shown in red hues. The bottom profile depicts the chargeability along the same line with low chargeability represented by blue hues and high chargeability represented by red hues. The electrical resistivity method allows for the characterization of resistive versus conductive targets, which can help determine the depth and lateral extent of anomalous features, sandy versus clay lithology, and potentially the water table. The IP method is a second-order resistivity measurement that quantifies the charge storage capacity of earth materials. The IP data help augment our understanding of any conductive anomalies, specifically moderately clay material, like sandy clay. The resistivity data indicate these anomalies have increased or decreased amounts of clay, which will help guide well placement. Unlike the simple 3-layer system described by the ephemeral Santa Cruz River floodplain, the combined resistivity and IP results are more complex in the San Pedro floodplain. After the resistivity and IP surveys, hole PB-2A was drilled along line 1 and was the deepest boring. 2 clay layers were identified from the drilling results and compared to the resistivity and chargeability. The soil description is shown as layers at depth on the left, and a graph of the resistivity and chargeability values at the same location is plotted on the right, with resistivity in red and chargeability in blue. At about 18 feet below ground surface, the resistivity decreases drastically and the chargeability increases. The low resistivity and high chargeability were correlated with a massive clay unit. The resistivity values increased at depths beneath this massive clay unit, shown in dark blue. The chargeability is slightly lower for the low clay unit. There appears to be a dampening of the resolution of these electrofacies directly beneath the water table, again shown at 18 feet depth in the location of this well. Although it would be convenient to characterize the soil characteristics and lithology of the subsurface based on the resistivity profile at depth or the chargeability at depth, we see that the combined analysis of IP data with the resistivity data provide greater information at depth to predict the lithology. However, the dampening noted on the previous slide proves difficult to establish a precise delineation of lithology from existing electrofacies. The dampening effects of resistivity and chargeability at depth beneath the water table are also evident along the fourth line of our survey. We compare the drilling results with geophysical data at the same location. Curiously, within the electrofacies identified adjacent to the San Pedro riverbed, we see similar features in the electrical resistivity profile that we saw near the pre-1871 headcut of the Santa Cruz River. Note this feature in the circle above. Namely, the thicker near-surface resistive zone is adjacent to a conductive feature that approaches the surface. Seeing as the San Pedro River is a perennial flow and not an ephemeral flow like the Santa Cruz, the characteristics of the San Pedro resistivity profile may lend confirmation that the former headcut of the Santa Cruz was indeed located at the identified portions of the Santa Cruz study profiles. Again, the dampening of the two electrical properties occur below the water table. However, in this case, we have identified the massive clay at depth beneath an elevated low clay zone. Each of these characteristics were defined by the comparison of high versus low resistivity and high versus low chargeability. The combined analysis of the electrofacies of the two electrical geophysical surveys over the San Pedro floodplain can corroborate drilling results when high and low zones of resistivity and chargeability are assigned to variable clay content. The electrical resistivity and chargeability properties provide a broad characterization of electrofacies in both project areas, the Santa Cruz and the San Pedro alluvial floodplains. The characteristics of electrofacies of the perennial flow of the San Pedro may give clues to the historical paths of river flow within the floodplain of the now ephemeral Santa Cruz River. Drill log lithological analysis is sensitive to grain size distribution, whereas the resistivity measurements are sensitive to contrast in electrical properties. The discrimination of the lithology along a survey line using electrofacies is contingent on the electrical contrast of the lithofacies. Electrical resistivity and IP provide spatial continuity of data at depth, which would be cost prohibitive to survey with drill hole data alone. In summary, electrical resistivity and IP surveys can further inform the extent of sediments within a floodplain system. The combination of the two methods can further inform the siting of wells within a survey area. Contrast in electrofacies and sediments may further inform the presence of historical headcuts of rivers. The identification of historical stream channels may further inform the locating of better producing water wells. For further discussion, feel free to email the address below. Thank you for listening.